So people started to think about what is this term? What is this ui prime, uj prime bar? The first thing um, is the unit of this term, meter square per second square, which is the same unit with stress, right? This is the same unit with the stress. And similar to viscous stress that we had, so people thought if it is a stress term, this means that on the fluid particle, because of these fluctuations, prime fluctuations, you see these fluctuations, okay? Because of these fluctuations in the flow field, additional forcings are generated that force the fluid particles to get deformed or get strained. And this is because of the presence of turbulence that we have fluctuations actually. So some people thought, okay, look at the solid people. They calculate stress from strain. Even in fluids, we calculate viscous stress from a strain. So if this mathematical artifact, if this ui prime, uj prime bar has the unit of stress, why can't we calculate it from a strain as well? So this is what we call a Boussinesq assumption. We will come to this Boussinesq assumption later, but all the effort people have been trying to do for the past 130 years is to build turbulence models that you choose in your CFD software, like K epsilon and K omega and others. And these models provide you additional equations just to be able to calculate this term ui prime, uj prime bar, so that your momentum will get modified, and you're hoping that if your model works well, you would get correct distribution of velocity and, let's say, pressure um, in your field of interest. So the question is how we model these things. Actually, the rest of this semester we will go into the details of understanding those models. But at the end of the day, we have spent all the effort just to model ui prime, uj prime bar. So we just wrote an equation for the uh, mean momentum equation, let's say, and this equation can be written in different forms. So it looks like the stress on the right hand side. So you have your uh, density, this is your acceleration, and this is your whole forces. So you have the forces in here. So it is the uh, ddxj of the pressure, which is your isotropic stress, and this is because of your viscosity, so it's called viscous stress. And the last part, we just said that it is its unit is stress, so we call it as a turbulent stress or Reynolds stress, because it is only happening in turbulent flow. So this minus rho ui prime uj prime is a second order tensor. So it has I and j, and it should have all the second order tensor properties, such as, for example, deviatoric part, or let's say isotropic part, and so on. This minus P delta I J is isotropic stress, so it's independent of rotation because it's isotropic, is independent of rotation or direction. Um, and this dui dxj plus duj dxi is actually double of your mean strain rate tensor. And if you look at this equation, which is in fact, it is three equations. It is a vector equation. In addition to continuity equation, we have in total four equations. And how many unknowns do we have in here? We have three velocities. So you have u1, u2, and u3 bar. And one you have one pressure in here, so you have p bar, and you have additional term, this ui uj, ui prime uj prime, and we don't know what this is, and we don't have any equations for this ui prime uj prime. So the system of equations is not closed right now. Without the averaging process, actually you saw that if it is not averaged, it was closed. So in the instantaneous conservation equations, there was no such a term. So you had three equations, and you had three unknowns there. So the instantaneous equations can never be solved. So without proper identification of exact initial conditions. And with the averaging process, it's easier to solve right now, you see. But given the fact that we could close the system of equations, so we need a fifth equation. So um, which should be a governing equation for the additional term, for this term, ui prime, uj prime. And we will see how can we deal with this closure problem in the coming weeks, actually. Okay, so uh, what we will do is we will start talking about some of the things that you probably read in your second paper. And those some of the things are, for example, we will um, first discuss about the scales of the turbulent motion. We will define what an eddy is, and after that, we will try to understand what we call the energetics of the flow, and what will be the conservation equation for the mean kinetic energy and turbulent kinetic energy, and how are they related. How does energy transfer between the scales from the large eddies to small eddies? And we will actually follow what Kolmogorov did, and starting with the small dimensional analysis, and we will try to understand what is the actual smallest scale that we can encounter in a turbulent flow field, which today we call it as Kolmogorov length scale. So you may remember in the very first presentation that I showed you in the beginning of the semester, there were few people and the names of scientists that actually worked on turbulence. The Reynolds, then G.I. Taylor, and Kolmogorov and Richardson. Louis Richardson was the first person who described the phenomenology of turbulence. What does it mean? It means that the turbulence geometrically is composed of eddies. So these eddies that we are showing here in this diagram, large and small size eddies are there. If by some mean there is a mechanism that leads to turbulence generation in the flow, the turbulence sucks in the mean kinetic energy, uh, or let's say it reduces the mean kinetic energy of the flow. We realize this as loss. So we say we have lost total pressure, for example, in turbomachinery. What we actually mean that we lost total pressure is that the mean kinetic energy of the flow is reduced. Where does it go? It goes to feed in the turbulence. So as what you see as injection, okay? It goes to feed in turbulence. So there is an energy flow that is generated at large scales. These are the large scales, okay? And it is due to presence of solid bodies, for example, boundary layers or walls or so. And this energy flows through turbulence. Turbulence is composed of eddies. So from large eddies to smaller eddies, the energy is getting transferred. So you have a flux of energy. Since it is transferred from large to small eddies, from a very large to very small eddies, the energy gets transferred, and since it is getting transferred, we call it the energy cascade. So cascade, shelale, cascade is the energy from top to bottom. Okay, so this is water that is coming from top to bottom. So this is called the cascade of the energy. And this is what Richardson defined back in 1922, actually. So Richardson says that turbulence can be considered to be composed of eddies of different sizes. And time, by 1922, we have to define uh, mm, also what an eddy is, because he used eddies in his words. So when we talk about an eddy, it could be a small vortex. So all vortices can be considered as eddies, but not all eddies are vortices. Just keep it in mind. An eddy is a coherent structure. It does not have necessarily circular shape. It can be hairpin vortices. You remember the eddies that I showed you in the previous session coming out of a jet. There was an animation on that. So eddy is a turbulent motion. By definition, it's a turbulent motion localized within a region of size L, this size L in here, that is at least moderately coherent over this region, over L region. So when we talk about an eddy, the most important characteristic is its size, its L size. If you're talking about a turbulent wake behind a cylinder, in here, for example, the cylinder will have a certain diameter, right? This is the diameter of the cylinder. So the following graph shows the laminar and turbulent flows and their characteristic Reynolds numbers. And you look in here that actually I have taken this graph from Dynamical Systems Approach to Turbulence from Thomas Bohr et al. And you see that if the Reynolds number is high enough, the wake will be turbulent. So you see that in here and in here you have a turbulent wake. And there will be turbulent vortex shedding as well. So these are not actually in here. You have laminar vortex shedding, as you see, but in these cases you have turbulent vortex shedding. And what's the size of the largest eddy that can possibly be, and what's the size of the smallest eddy in that kind of wake, for example? Therefore, you have to define some length scales that are generally associated with eddies. So we call this L as the length scale associated with an eddy. And why we call them coherent, we said it is coherent. Eddy is moving with the flow, and while moving, it can change its shape. So it can be distorted, but it moves with a certain velocity, and this certain velocity is not necessarily the mean velocity of the flow. And due to its characteristics, it can move with its own velocity. So Not only its size is important, we generally characterize its velocity as well. So there could be a characteristic velocity which can be obtained from experimental results or simulations. So once you have your U and your L, you can define the characteristic time scale as well. So this characteristic time scale is nothing but L divided by U. Okay. In the turbulent flow, the largest eddies that can be present in the flow field with length scale L0 are generally in the order of magnitude of the largest length scale of your geometry. Okay, so if a scale of the largest length in the geometry is L, this L0 is actually um kind of defined by your capital L, which is from your, which comes from your geometry. So, for example, in the circular cylinder wake, the largest length. What is the largest length? It's the diameter of this cylinder. So probably the largest eddies that can in your flow domain are in that order of magnitude. Are not, let's say, if this is 1 meter, it doesn't mean that the largest eddy is 1 meter. It is in the meter order of magnitude. If you're talking about an airfoil, in here you see that airfoil is generally characterized by its chord or its thickness, okay, maximum thickness. Depending on the flow regime, meaning that if it is not separated, if it's not separated, if it is going like this on an airfoil, um, and we have a very well behaved attached flow, the boundary layer, all those boundary layers are attached, and the upper boundary layer and lower boundary layer on the airfoil will merge and then generate the wake of the airfoil. So probably the largest eddy size will be proportional to the maximum thickness in here, thickness of the airfoil. But if it is fully separated flow, if it is turbulent and fully separated flow at very high angle of attack, your chord will be more relevant to your largest, let's say, geometrical scale, length scale. So those geometric scales, like the chord, like the maximum thickness, and like the diameter of the cylinder, determine the largest eddy size, and we generally call it as the integral length scale. The velocity scale for the largest scales is generally in the order of magnitude of the fluctuation level of the flow. So this is very important. The velocity scale is the in the order of magnitude of fluctuations, and you could have a mean velocity behind a wake of cylinder or airfoil, but you could have fluctuations which depends on the Reynolds number. So the motion of the eddies determines the order of magnitude of the eddy velocity, and it's generally in the order of u prime. And you say that your u0, like the L0, we defined u0 in here for the velocity, is in the order of magnitude of fluctuations, which is nothing by 2/3 of your turbulent kinetic energy, a square root of that. So the K is your turbulent kinetic energy. The fluctuation U prime could be in the order of the mean velocity. It could be in the order of mean velocity as well, but it depends on the geometry. They may not be very small. And so this means that eddies can be moving as fast as free stream velocity, but generally they cannot move actually faster than the free stream velocity. And using these definitions, you can define the Reynolds number for the largest eddy size. So when you put subscript 0, it means that the largest eddies. So Reynolds number based on the largest eddy size is defined as U0 L0 over nu. And this Reynolds 0 is generally a very big number. So what happens is we know that at high Reynolds numbers, some instabilities are created. So when you have your instability, it means that your viscous forces are smaller, very, very smaller than your inertial forces, as you saw in the uh, presentation of Osman as well. So the Reynolds number is actually um, a comparison between the inertial forces and the viscous forces. So when your, let's say, viscous forces are very, very smaller than your inertial forces, some unstable condition happens. So actually, high Reynolds number is a source of instability, and Reynolds number determines the transition. High Reynolds number means that inertial effects over viscous effects are dominant. So the general damping in your system is low compared to its inertia. And this means that your system is prone to instabilities. And in this case, the largest eddies are also prone to instabilities. They cannot stay, meaning that if in the wake of a cylinder a large eddy is created, it cannot remain large for a long time. Okay, this large eddy that is created, it cannot remain for a long time, and it will become unstable and it will start breaking up. Okay, so large eddies are unstable and they start to break up. The large eddy breaks up into two parts. Okay, now we have two eddies. And if the Reynolds number is still large enough for the size of these two broken eddies, they will also break up. So they also broke up. And if the Reynolds number is still large enough for these eddies, they will also break up. And it will continue until such a level that um, the Reynolds number associated with the eddy size, with this size of the eddy, is not high enough, so it cannot cause the instability anymore. When there is no instability, the only physical mechanism is dissipation, and they will just vanish. Okay, after the certain size they will just vanish, and their energy will be converted to heat. So what we are always after is, what is this smallest scale, length scale at which energy is dissipated to heat? So this is always a question for us. Okay, um, let me stop the recording and I will start in a second. So the energy is transferred during the so-called breakup process. And when the largest eddy breaks up into two, normally one could assume that this energy is get splitted equally into two. So it is breaking, and I can expect it's equally. But in reality, in experiments which were done in 1990s, especially by Charles Menewell and at Johns Hopkins University, we understood that the energy does not get split evenly. One of the eddies always gets more energy, and we will talk about that in energy spectrum as well. In any case, this energy is transferred to a smaller eddies. And this will go on until we reach a certain point at which the Reynolds number is not high enough, and we have reached the smallest length scale in the flow field. If we calculate this Reynolds number, it will be very small, and meaning that these smallest eddies are in a very laminar environment. Although the flow field could be very turbulent, but at this scale, everything is very laminar. And Reynolds number there is in the order of 1. So uh, at this point, viscous effects or the damping or friction are very dominant. You can think about a little vortex, and this vortex is trying to rotate and somehow convect its motion, but if its kinetic energy is not sufficient enough to overcome the whole friction around it, which is due to a strong viscosity, it cannot just rotate and it will stop. So it will dissipate its coherence and finally it will vanish. So here we have what we call as a dissipation. So energy dissipation happens in here. Dissipation to heat. And we generally use the Greek letter epsilon uh, to characterize what the dissipation rate is. Dissipation rate means uh, mm, during the breakup process, the energy gets transferred from large eddies. As we said that you have the injection of energy from mean flow. So here you have the mean flow, and it is injecting energy to the turbulence. So you have this energy that is getting transferred from large eddies all the way to a small eddies, and the energy is flowing like a cascade or waterfall. And the dissipation rate means how fast are you losing this energy. So energy is kinetic energy, so its units is meter square per second square. Okay, energy is meter square per second square, and how fast you are losing your kinetic energy is means that per second how fast. So you will get the actual unit of epsilon equal to meter square over second cubed. So this is a general description of turbulence as we know it today, and the fact that it is composed of different scales, the fact that eddies break up and energy gets transferred, and the fact that energy at some point will get dissipated. So this is everything that we know from turbulence. The thing is, the amount of dissipation rate, although it physically occurs at a smallest scales, but it is determined by the largest scales. So your epsilon is determined by the first process in the cascade sequence. In other words, the breaking up the largest scale or transferring energy from the largest eddies. We already talked about L0, U0, which are the integral length scale and velocity scale of largest eddies. And the time scale of the largest eddies is tau 0, which is L0 over U0. So the energy level of the largest eddies will be proportional to U0 squared, right? Because energy, like it's a kinetic energy, so one half of mass times velocity squared. So the energy level is proportional to U0 squared. So the epsilon should have an order of magnitude of energy over time. So you can write this as uh, the energy for u0 squared for the energy and the time scale, tau zero for the time scale. So let me repeat it again. Dissipation occurs at small scales. Okay, these smallest scales, the dissipation occurs here. When we say dissipation rate, we mean the amount of losing energy in 1 second. But actual numerical value of this amount is determined not by the smallest scales, but by the characteristics of the largest scales. Because that total energy that gets transferred and is dissipated through the cascade is constant. So you have a amount of energy that is injected into the let's say uh, eddies. So this total amount of A is being transferred to the dissipative scales and it is dissipated to heat. That's why your epsilon or the dissipation rate is determined by this size of the largest scales. So this epsilon that you're seeing in here, this epsilon that you're seeing in here is the one that you use in turbulence modeling, for example, in K epsilon models. So you can estimate the order of magnitude of energy dissipation in your flow field just by having your U0 and L0 values. This means that if you know what kind of flow you are dealing with, is it a cylinder or airfoil or a flat plate? So you have some idea about L0, I just told you, and you would have some idea about the fluctuation levels, U0, right? Then you can estimate your epsilon. Again, it's not calculating, it is estimating. We will get back to this dissipation in a more quantitative manner later. Now, we want to go into equations a little bit. We talked about energy, which is generated at the largest scales and actually not generated, it is being transferred from the mean flow and it will being transferred again among the eddies. So um, we need to understand what equations actually govern this energy transfer of the largest eddies. How is energy transfer represented? In order to understand this, our starting point is momentum equation, and we will use average momentum equation for incompressible flow. So, as a reminder, you had this equation, average momentum equation, and this says that the change of forcing or uh, gradient, let's say gradient of all the stresses will result in a change of a momentum, which we know it as an acceleration or deceleration of a fluid particle. So you know that this Reynolds stress tensor or turbulence stress tensor is a symmetric and second order tensor. It has, why is it symmetric then? Because just remember the fluid mechanics. If you have a fluid element and it was there is a stress on this side because of the balance of the stresses, there should be the same amount of stress but in the opposite of direction, in the opposite side of opposite face of this. So it means that uh, ui prime uj prime is equal to uj prime ui prime. So when you put it in the matrix, it means that it's a symmetric matrix or symmetric second order tensor, and it has diagonal components which we call as normal stresses. You remember again, those normal stresses are stresses that were on the uh, normal plates. So these are the normal stresses, if you remember. And it has off diagonal components, which we call them as shear stresses. So normal stresses and shear stresses. Of course, you can always diagonalize a second order tensor, and you remember how to diagonalize a second order tensor. If you had a matrix of 9 values, if you want to diagonalize this matrix, meaning that all the off diagonal components will be zero and only you have these diagonal components as a value, you had to use, you had to find its eigenvalues. And the eigenvectors then will give the principal axis of the stress tensor along which there are no shear. So if you are not writing the tensor in its principal axis, you will end up with off diagonal components which represents the shear stress. Uh, we define turbulent kinetic energy equal to half of ui prime ui prime, which is equal to half of the trace of this Reynolds stress tensor. And there is one simplification, and it is if the fluctuations are isotropic, so meaning that there is no directional preferences. In this case, there will be no off-diagonal components, regardless of whether you are in principal axis or not, because it has to be independent of rotation of axis when it is isotropic. Okay? And in every axis system, it should give the same result. Therefore, there will be no shear stresses, and all you have are the normal stresses. So we just do some simplification. And the second property for the isotropic fluctuation is that your u prime squared bar and v prime squared bar and w prime squared bar are equal. Just to visualize what we mean by an isotropic field, I just drawn two sketches of isotropic and anisotropic fields. So this is u prime versus v prime. Uh, the only two components of fluctuations are, let's say, given in here, u prime and v prime. In any turbulent flow field, you could measure u prime and v prime. If the flow field is isotropic, you will get more or less a distribution like this left figure. And there will be no directional preference. So u prime, v prime is basically like a circular distribution. And you could generate isotropic homogeneous turbulence in the laboratory. But in most of the real applications, you could never generate this ideal case. This is very ideal, the isotropic turbulence. The, but it will help us theoretically to simplify equations and to understand the very fundamental nature of turbulence. But in real applications, we can never have isotropicity because you have real geometries which are not 100% symmetrical, and there will be some directional preference like the right figure. So if you measure u prime and v prime in a real flow field, it could be similar to this anisotropic case that I'm giving to you. For isotropic case, for this simplified case, the circular distribution, u prime v prime bar is equal to 0. So physically, the u prime v prime bar is a stress term, okay? But mathematically, it's a correlation function. You remember that it's a correlation of u prime with v prime. In other words, the correlation of u prime v prime is equal to 0 for isotropic field. And what I mean that you're trying to correlate u prime and v prime, and the figures are a way to show the correlation as well. So in the isotropic case, u prime and v prime are equally likely to be negative or positive. With the same probability, they both are positive and negative. With the same probability, one is negative and the other is positive, like in this quarter, in this quarter. Okay, with the same probability, they both are positive in the first quarter, or they both are negative in the third quarter. With the same probability, one is positive, one is negative in the second and fourth quarters. In other words, for an isotropic case, if your u prime is positive, look at this isotropic field, the two probabilities of having v prime negative and v prime positive are equally likely. And it applies for the u prime negative as well. But case, in an isotropic case, this correlation is not zero anymore. So it means that if your u prime is greater than zero, you can see the anisotropic field. It means that if your u prime is greater than zero, meaning that if you're here, your v prime is negative always, because you see no v primes in the first quarter. And if your u prime is negative, then your v prime is positive in here always. So what does it mean? It means that your u prime v prime bar is always negative. This is generally observed in turbulent flows, and there is a physical reason for this. So what I have drawn in here for u is a typical velocity distribution, and this part is very well explained in the Kunduz fluid mechanics book. You can consider a typical shear flow, meaning that we have a velocity gradient, and this could be part of your wake, for example, or part of your boundary layer, or a free shear flow. And there is a mean velocity difference as you travel along a y direction in here. Now, uh, we we do a hypothetical experiment. Imagine a fluid particle at some point at certain height, for example, at this height, y minus dy, there exists a certain particle. And this fluid particle is trying to move within this shear flow because of the velocity gradient. So instantaneously, because of the turbulent motion, this fluid particle can get kicked up to an upper level, right? Because of the shear. So some disturbance, some motion, some eddy can come and hit this particle, and it moves up instantaneously, right? To an upper level, which could be level Y. Now, getting an instantaneous kick means it gets an instantaneous velocity fluctuation along y. So velocity fluctuation along y means v prime. So it is getting v prime as a positive. And at this upper level, the mean velocity, what is the mean velocity? What is the u prime at this upper level? It is higher, as can you see in here. So in here it has this much velocity, in here it has this much velocity. So at y, its mean velocity is higher. So its new mean velocity is different than its original mean velocity, right? So what will happen is this particle will try to reduce the axial speed, because the mean velocity is happening in the axial direction. It tries to reduce the axial speed at this upper or higher level because of the fact that it has lower momentum than its environment at the new level, right? Because it is just transferred from lower level to higher level, so its momentum is lower. And since it wants to reduce the axial velocity, it will cause a negative velocity fluctuation in x direction. So it has negative velocity fluctuation. Therefore, when your v prime is positive, that it kicked up causes a negative u prime. And you can also think the opposite when, let's say, uh, the opposite way that you have when your particle is kicked down from y to y minus dy as well. So the fact that u prime times v prime bar is negative most of the times would have an impact on the energy cascade. In order to understand and see this impact, we will go to energetics, meaning the general understanding of the energy interaction between the mean flow and the turbulent flow. So we already said that mean flow loses some of its energy through the energy cascade. So we want to understand how this actually happens. So I think this would be enough for today. So next week we will start the energetics of the mean flow and also energetics of the turbulent flow. So we will see how energy actually cascades from mean flow to the turbulent flow. Thank you for your participation and consideration, and see you next week. Have a good day.